Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we discuss Module 2, which is entitled Addition and Subtraction of Whole Numbers. And what we're really going to be doing is looking at two things. One is how we combine groups of tally marks to form bigger groups of tally marks, and how we record that. And the second thing is that we're going to pay particular attention to how place value helps us do this, especially when we remember our central theme that numbers in this course will always, unless otherwise specified, be adjectives modifying nouns. That's very, very important. You know, I'm reminded of a story back in the late 50s when America wasn't quite as liberated, when the novel Lolita came out, in which a 40-year-old professor falls in love with a 12-year-old girl. An American is trying to explain the story to a French friend. And he said to the friend, "Did you read Lolita?" He said, "No, what's it about?" And the American said, "Well, it's about a 40-year-old man who falls in love with a 12-year-old. And the Frenchman looked and said, "A 12-year-old what?" You see, the difference of what we're modifying here can be very, very important. And we're going to see that in just a moment. But what I want to do now is to show you how we go from tally marks to place value and learn to keep track of tremendously large numbers of numbers being shifted around. Let's take a look at the board here, and let's just look at a fairly simple situation. What I've written here on the board is 3 tally marks followed by 2 tally marks. That actually is a complete sentence in the language of tally marks. What it says is that this many and this many are this many. In other words, this many and this many more altogether give me this many. A very simple statement. A statement that most likely any youngster of 3 or 4 years of age would certainly understand. Notice that we would never dream, I hope, of even trying to do something like this. This would be a rather silly thing to do. It's unnecessary to have a plus sign here and an equal sign. All we're saying is what? This many and this many give us this many altogether. You see, whether you're using tally marks or Roman numerals or Egyptian numerals, addition is done just by amalgamating the symbols. If you take 3 tally marks and put 2 tally marks right next to it, you have 5 tally marks altogether. But now when we get to, see, we don't write this, but when we get to the language of place value, now you see here comes a new artificial language, 3 plus 2 equals 5, that says exactly the same thing that the tally mark said. But now it's more sophisticated, and it requires that we learn some more vocabulary terms. First of all, when we write this, we call the process an addition problem. And the answer following the equal sign, the 5 over here, is called the sum. The sum is the answer to an addition problem. The numbers being added are either called terms, addends, or summons. Historically, they were called addends and summons, but since most people who take arithmetic ultimately go on to at least elementary algebra, I prefer the word terms because that's the language that carries through in the subject of algebra. But all of these mean the same thing, and they're emphasized in the textbook, and you'll get plenty of experience using them. But look at how this artificial language works. You see, if you don't understand this language, you don't know what this means. Yet if you do understand the language, all it says is that this many and this many more is this many. That's all it says in the language of tally marks. But you see, when we use place value numerals, something very exciting happens. And the exciting thing that happens is that as long as one of the numbers that we're adding, one of the numerals, is a single digit, it's very easy to perform the problem. See, addition is easy if at least one numeral, remember numerals are the symbols that denote numbers, if at least one numeral is a single digit. Look, for example, at the problem 39 plus 3. What I could do is to write 3 blanks, and now I say what? I'll start with 39, then I write 40, 41, 42. Sort of like we count on our fingers. 39 plus 3. You see, 40, 41, 42. Notice, however, that if you reverse the order, the problem seems somewhat more difficult. Look, for example, at trying to do the same problem, putting the 3 first. 3 plus 39. In fact, if you ask this problem of a youngster, the youngster can probably do the one we just did, the 39 plus 3, because the youngster tends to do the arithmetic in the order that the terms are mentioned. When you say to the youngster, how much is 3 plus 39, the youngster says 3, then doesn't have 39 fingers to put up. Well, hopefully doesn't have 39 fingers to put up. The problem becomes much more complicated that way. However, there's a remarkable property that we have when we deal with tally marks. Namely, when we deal with tally marks, 3 plus 2, for example, is the same as 2 plus 3. In other words, if I have this many tally marks, I certainly don't change the total number just by shifting them around. You see, here I have 5 tally marks, and here I have 5 tally marks. So when I want to solve the problem 3 plus 39, I can write that problem as 39 plus 3 and do the problem in that order. Okay? And by the way, beware. In real life, order often makes a difference, but not in addition. That's interesting. See, for example, does it make a difference whether you say, first I undress and then I shower, or whether you say, first I shower and then I undress? And by the way, I'm not passing judgment. Do it whichever way you like. All I'm asking you is, do you recognize that whichever way you do it, the other way is different? See, but in general, even though order makes a difference, when you add, you have the luxury of changing the order without changing the answer. And because of that, we give that property a very special name. And what we say is that addition has the commutative property. Commute, like to move. Commute means you can change the order. That's a very, very important thing that we can use with addition, and we'll come back and talk about that in more detail as we go along. But there's a more important point. You know, if I should open up a program or a discussion with an anecdote, I will never do it unless I'm going to use that anecdote as a learning experience. I'm now going to show you something that will simplify all of arithmetic. I'm going to show you that if you can add any 2 single digits, and that's why in elementary school we memorize the addition table for single digits. If you can add any pair of single digits, you can add any number of place value numerals, no matter how many digits are in them. And the key point is this, and it's something very, very important. I can't stress this enough. And that is, when you say that 3 plus 2 is 5, you are assuming that 3, 2, and 5 are adjectives modifying the same noun. And don't underestimate that. That is going to come back not just here, but throughout our course, throughout algebra if you go on with me, throughout even calculus. This is a very, very important concept. And you already know it. For example, 3 nickels plus 2 nickels is 5 nickels. We all know that. 3 dimes plus 2 dimes is 5 dimes. See, how do we do that? We say 3 plus 2 are 5. See, 3 plus 2 are 5. And then what do? We just keep the common noun, which is nickels. See? 3 nickels and 2 nickels are 5 nickels. We don't say 3 and 2 are 5, and a nickel is a dime. No. When you add the adjectives and keep the common noun. Now, what happens when you have 3 dimes plus 2 nickels? You see, 3 and 2 are 5 only when 3, 2, and 5 are modifying the same noun. For example, 3 dimes are 30 cents, 2 nickels are 10 cents, so 3 dimes plus 2 nickels is 40 cents. Or you could have said, hey, isn't 2 nickels the same as a dime? And 3 dimes plus 1 dime is 4 dimes? Sure, you could have. And now watch what happens. If you were to now leave out the nouns and just leave in the adjectives, look what happens. 3 plus 2 is 40. 3 plus 2 is 4. You know, if a teacher says to a little kid, how much is 3 and 2? And the kid says 3 what and 2 what? The teacher usually will think the little kid is being a wise guy. And yet the fact remains that what? If you want that answer to be 5, 3 and 2 had better be adjectives modifying the same noun. And don't you do that all the time? If you get a report card and you have 3 A's and 2 A's, and somebody says, how'd you do? You don't say I had 3 A's and 2 A's, you say I had 5 A's. And you don't say I had 3 B's and 2 B's, you say I had 5 B's. But what if you get 3 A's and 2 B's? You don't say I had 5 A B's, you said I have what? 3 A's and 2 B's. Whenever you added up your grades, for example, you are always only doing what? Adding the like denominations. And you may say, well, why is that so important? Well, the reason it's so important is that if you keep that in mind, once you know that 3 plus 2 is 5, you now virtually know millions of number facts. For example, you now know that what? 3 million plus 2 million is 5 million. Because you see, 3 plus 2 are 5, and we're modifying the same noun. 3 million and 2 million are 5 million. And watch how the language works over here. See, isn't this simple? Do you see what I'm saying over here? You see, all you have over here is 3 plus 2 is 5, and the rest is taken care of by the fact that 3, 2, and 5 are modifying the same noun. Look what happens, though, when you write this in place value. Suddenly, the problem looks much more complicated, because you see, now the zeros have to hold the place to tell you that the 3 and the 2 are in the millions place. So now when you write this, 3 million plus 2 million is 5 million, doesn't that look like a problem for 7-year-olds if this is the problem for 5-year-olds? And yet this is what? Just a different language for saying this. This is no more than knowing that 3 plus 2 is 5. But you've got to be careful. The 3 and the 2 still have to modify the same noun. Look at this one, 3,000 plus 200. See, 3 plus 2 is 5, but you're not adding the same noun. And you see what we do over here? If you elect to use place value numerals here, see, we would write 3,000 like this. And by the way, this is a very small point, but notice how I expect that before you go to a new module, you've mastered the old module. In other words, in Module 1, we talked about how you developed writing 3,000 as 3, 0, 0, 0. Once we develop a module and you're able to do the self-test, we will just assume that that module is a given whenever we do future modules. But getting back to this, you see 3,000 looks like this. What does 200 look like? The 2 has to go in the hundreds place. So 3,000 plus 200 is neither 5,000 nor 500. It's what? 3,200. In fact, the answer is just read this, 3,200. But as soon as we know that the adjectives are modifying the same noun, we can now add any number of digits together. Look at this particular problem. 2,123,406,123 plus 1,256,593,754. And before we even tackle that problem, just try to visualize this in terms of tally marks. Look at how powerful place value is. But now comes the even more powerful part. Suppose you have learned, either by understanding or by memory, the arithmetic for single-digit addition. This 10-digit addition problem becomes 10 single-digit problems. Look what you do here. Assume you've learned your tables now. You say what? 3 plus 4 is 7. Or could you have said 4 plus 3 is 7? Doesn't matter which way you do it, because addition is commutative. You can even do it on your fingers if you don't remember the tables. You could say 4, 5, 6, 7. But the important thing is, the reason you're allowed to put the 7 here is that by placement of the digits, 4 and 3 are both modifying ones. You're saying 3 ones and 4 ones are 7 ones. For example, the one thing you don't want to do is to say, hey, 3 plus 5 is 8, so I'll put an 8 over here. No, you don't do that. Because you see here, the 3 is modifying ones, the 5 is modifying tens. By lining the numbers up so that the digits in the same denomination match, you see, then you can do this. Why can you say that 2 plus 5 is 7 here? Because 2 tens and 5 tens are 7 tens. 100 and 7 hundreds are 8 hundreds. 6,000s and 3,000s are 9,000s, etc., etc., etc. You see, I'm only adding 2 single digits at a time. By the way, notice also why you have to learn the table for 0, because in place value numerals, the 0 will appear, so you should know the number fact that what? 9 plus 0 is 9. See, but you see how these line up? You've got to have them lining up by correct denominations. Now, also in our last discussion, we mentioned that there's no such thing as a free lunch. That whenever you bring in something new that's powerful, it's conceivable that you're going to have serious side effects. And one of the side effects we talked about was that when you use place value, you're never allowed to have more than a single digit per place value column. Now watch what happens. Let's suppose a youngster has learnt the addition tables, and the teacher now says to the youngster, and maybe you've done the same thing, or maybe you've wanted to do the same thing, how much is 56 plus 78? What do you think the average youngster does? The average youngster from the table says, hey, 8 and 6 are 14, 5 and 7 are 12, and writes this down as the answer. And the teacher marks it wrong. And you say to the teacher, why did you mark it wrong? And the teacher says, because the answer isn't 1,214. But the kid didn't say the answer was 1,214. It just looks like that. It's confusing, isn't it? You see, what the youngster really said, and to see it more clearly, let's put the labels back in. See, 56 is 5 tens and 6 ones. 78 is 7 tens and 8 ones. Isn't it true that 8 and 6 are 14? And 5 and 7 are 12? In fact, in terms of money, if you have 6 $1 bills and somebody gives you 8 more $1 bills, do you have 14 $1 bills, or is there a flash of lightning and a clap of thunder, and lo and behold, the 14 ones turn into a 10 and 4 ones? No, you have 14 ones and 12 tens. And if you want to, you can exchange 10 ones for a 10, but you don't have to. In other words, you can say what? I'll keep 4 of my ones, excuse me, and trade in 10 more for 1 more 10. And now you say what? The answer is 13 tens and 4 ones. And then in the next step, you can say, okay, now I'll take 10 of my 10s and trade them in for 1 more 100. So the answer is 134. Notice, going back to this, that if we had drawn a line like this and said the answer was 12 tens and 14 ones, that would have been the correct answer. Now the question is, how do we keep the simplicity of this while we get the correct answer of this method? And this introduces a place value technique that's called carrying. And what you say is something like this. You say 8 and 6 are 14. 14 what? 14 ones. But we're only allowed 1 digit per place value column. So we say, okay, we'll keep 4 of the ones and trade in 10 for 1 more 10. And the way we say this fast is we say 6 and 8 are 14, put down the 4 and carry the 1. You see, 4 ones and a 10. 4 ones and 1 more 10. Then you say what? 7 and 5 are 12. 12 what? 12 tens, and 1 more 10 is 13 tens. And now suddenly the answer is 134. You see the idea here? And by the way, if you were using, for example, the Egyptian numerals that we talked about in the last lesson, you wouldn't have to carry. How would you write 56 in the Egyptian numerals? You would use 5 arches and 6 tally marks. And how would you write 78? It would be 7 arches and 4 tally marks. And now what would the answer be? This is it. It's this many tally marks and this many arches. And if you want to trade in 10 of one for one of the next denomination, you can, but you don't have to, because the nouns are still visible by virtue of the symbols that represent them. Now there is one new thing that happened here that I don't have the right to do unless I establish the validity with you. We did something in doing this problem by place value that wasn't in our tables. Do you remember that in our tables we never add more than 2 single digits at a time? Look what happened back here. We said what? 7 and 5 are 12 and 1 is 13. How many digits were here? 3. We don't have tables for 3 digits, but the beauty is that there is another property of addition that says, hey, it doesn't matter how many digits we have to add, we can always add them 2 at a time. There are many things that we can do that way, that we can do 2 at a time. Do you know that? For example, if I want to find the tallest person in the room without lining everybody up, all I have to do is take any 2 people. I look at the first 2 people, whichever one is the taller of those 2, I keep. Then I compare that person with the next person, and the taller of those 2 I keep. And I keep on going this way, comparing 2 at a time, always keeping the taller one, and when I get to the end, the one that's left is the tallest of the group. In other words, no matter how many there are in the room, I can test for height, for age, any one of a number of properties simply by doing what? Looking at people 2 at a time. You see, let's take a look at this over here. You see, here's 1 plus 5 plus 7. And all I'm saying is, if I visualize the 1 tally being pushed together with the 5 tallies, that would give me what? 6 plus the 7, which is 13. On the other hand, if I imagine that I'm going to take the 5 tallies and push them closer to the 7, you see what I'm saying over here? This was 1 plus 5, then I add the 7. This says 5 plus 7, which is 12. Then I add that on to 1. Don't I get the same answer in each case? You see, when I see 1 plus 5 plus 7, there are 2 ways I can read that. I can read it as 1 plus 5 plus 7, or 1 plus 5 plus 7. That's called the voice inflection property. In my son's weekly reader, when he was in the 5th grade, there was a little joke. One kid says to the other kid, "Did you ever see a man eating shark?" And the kid says, "No, but once in a restaurant, I saw a man eating tuna." See, notice in the phrase, man eating shark versus man eating tuna. The man eating is one word in the first phrase, but in the second phrase, it's what? Man is eating tuna. But man eating modifies shark. Well, let me give you another example. I wrote down the same sentence here twice because I claim that as you look at this sentence, there are 2 different ways that you can read it. For example, you could say what? It could be a very tall building. This could be what? The high school building, in which case you would put a hyphen between the school and building. Or it could be a one-level, a one-story building with grades 9 through 12 called what? The high school building. You see, depending on where I put my voice inflection, I have either what? The high school building or the high school building. And they mean different things. By the way, in mathematics, we don't use a hyphen. What we do is we use parentheses. If we want something to be treated as one word, we put the thing into parentheses. And all we're saying is that whether we use the voice inflection 1 plus 5 plus 7 or 1 plus 5 plus 7, the answer in addition is always the same. And the way we say that is addition has the associative property. See, we can associate the terms in any order that we want. You see, commutative says we can change the order. Associative says we can change the grouping. So to show you what I mean, I've taken 3 4-digit numerals in place value, and now I'll show you how we add them. See, all we say is what? 6 and 8 are 14, and then 14 and 7 are what? 21. Put down the 1 and carry the 2. And sometimes a person will say, well, I don't remember that 14 plus 7 is 21. Well, you say, look, just say, hold up 7 fingers. 14, 15, 16, 17, 18, 19, 20, 21. You see, as long as you're only working with a single digit, you can use your fingers if you have to. After a while, you get tired, and you learn to remember these facts. Also, you could have added in a different order. You could have said 7 and 8 are 15, and 6 are 21. You remember, addition is associative and commutative. You can change the order, you can change the grouping, as long as you're always adding what? Like denominations. See, what you really said over here is that we had 7 ones, 8 ones, and 6 ones. That's 21 ones, which is 1 1 and 2 more 10s. Then we said 2 10s and 8 10s are 10 10s, and 5 10s are 15, and 4 more 10s are 19, so we keep 9 and we carry 1. Then we say 1 and 9 are 10, and 2 are 12, and 9 and 7 are 19. And why can we add this way? Because the 1, 9, 2, and 7 are all modifying hundreds. We carry the 1, we say 1 and 8 are 9, and 4 are 13, and 2 are 15, and we get 15,991 for the answer. And compare that with trying to write down all of these tally marks. By the way, let me just take a minute or so to teach you some new notation. Do you know where the equal sign came from? Notice that in an equal sign, both these are parallel. You see, there's equal spacing at both ends. So whichever number you put here and here, since the spacings are equal, we say the numbers are equal. To indicate that one number is smaller than another, we pinch the 2 lines together so that the smaller number comes next to the smaller space. Of course, some people say, how do you know that these are pinched together? How do you know you didn't make a sloppy equal sign? So the way we avoid that is at the end where the smaller space is going to be, we pinch them together all together so that what? The lesser space is no space at all. You see it looks like an arrowhead now? So the lesser number goes on the side of the arrowhead, the greater number goes on the other side. You see the lesser number with the smaller space. And now I want to show you why it is so important to treat numbers as adjectives modifying nouns. You see, the numbers 8,987, 4,258, 2,476, those are four-digit numbers that are hard to keep track of. But if you were counting by thousands, wouldn't 8,987 come between 8,000 and 9,000? See, if you were counting by thousands, 8,000 would be too small to be this number, 9,000 would be too big. So in terms of counting by multiples of 1,000, 8,987 is more than 8,000 but less than 9,000. In a similar way, 4,258 is more than 4,000 but less than 5,000. 2,746 is more than 2,000 and less than 3,000. Do you see what I'm saying? If you're counting by thousands, you say what? 1,000, 2,000, 3,000, and someplace between 2,000 and 3,000 you jumped over this number. So now, isn't this an easy problem? 8 and 4 are 12 and 2 are 14. 14,000. 9 and 5 are 14 and 3 are 17. What does that tell me? Before I even start this problem, it says, hey, whatever this right answer is, it has to be where? Between 14,000 and 17,000. Those are called upper and lower bounds. That's a tremendous help. You say, hey, there's still a lot of room for error in here. Yeah, but there's a lot of room where there can't be an error. If by any stretch of the imagination you wind up getting an answer here that's either less than 13,000 or more than 17,000, you know it has to be wrong. That's called the number sense. See, even with a calculator, you could transpose a couple of digits and wind up with an answer which isn't even feasible. Because sometimes people say, well, you can afford to say 14,000 to 17,000 is a small range. I want a better range. In which case, we now do what we call measuring to the nearest thousand. You see, what we say now is, look, this number is between 8,000 and 9,000. What number is halfway between 8,000 and 9,000? 8,500. So anything in this range will be between 8 and 9,000, but closer to 8,000. Anything in this range will be between 8 and 9,000, but closer to 9,000. Where is 8,987? 8,987 is over here. That puts it where? Not just between 8,000 and 9,000, but between 8,500 and 9,000, which makes it closer to 9,000. In fact, there's a cheating way of doing this. There's a very quick shortcut. What you do is you're counting by thousands. All you do is look to the digit immediately to the right of the one you're counting in terms of. And if that's 5 or more, you just replace all of these by zeros and move this up by 1. And if it's less than 5, you replace these by zeros and just leave this the way it is. See, in this case, since this is more than 5, we make this a 9, then replace everything by zeros. And what that says is that 8,987 is not only between 8,000 and 9,000, but it's what? Closer to 9,000. Now watch what happens. See, rounded off to the nearest thousand, see, 8,987 is closer to 9,000. 4,258 is between 4,000 and 5,000, but since this digit is only a 2, which is less than 5, that means that this rounds off to 4,000 to the nearest thousand. 2,746 is between 2,000 and 3,000, but since this is a 7, which is more than halfway, this becomes 3,000. And now what this tells us is, look, not only is the answer between 14,000 and 17,000, but let's add over here. 9,000 and 4,000 are 13,000, and 3 more thousand is 16,000. Now we say what? The answer is not only between 14,000 and 17,000, but it's closer to what? 16,000. Wasn't our answer something like 15,991? I don't want to look back and see, but it was roughly something like that. Look at what we got without even adding. We pinned this thing down to say what? It's around 16,000. See? But be a bit careful when you round off. See, look at 11. 11 is between, when you're counting by tens, it's between 10 and 20. 12 is also between 10 and 20. 13 is between 10 and 20. 14 is between 10 and 20. So altogether, whatever this sum is, which happens to be 50, 11 plus 12 plus 13 plus 14, which is 50, without even adding, we know what? The answer has to be between 4 10s and 4 20s, between 40 and 80. But if we round it off to the nearest 10, see, 11 is between 10 and 20, but it's closer to 10. 12 is between 11 and 20, but it's closer to 10. 13 is between 10 and 20, but it's closer to 10. 14 is between 10 and 20, but it's closer to 10. If we round off this way, notice that if we round off term by term, our estimate comes out to be 40, even though to the nearest 10, the right answer is 50. And what you really want to say is, look, whatever this answer is, it's between 40 and 80, but closer to 40, which is exactly what 50 is. It's between 40 and 80, but closer to 40. You see, and that's the way we go about estimating numbers. Like if I say to you, estimate the sum 8,987 plus 4,258 plus 2,746. You see, that's the problem that we just did. That's the problem we just did. I want you to get used to the language over here. You see, the difficult part over here is that when you have everything in a horizontal line, it's very difficult to know for sure how these line up. See, because remember, we can only add if the adjectives are modifying the same noun. So one of the things that we have to do is to make sure that all of the denominations line up. So even if the problem is given in this order, if you were using a calculator, that's fine, leave it like that. If you don't have a calculator, then what you have to do is what? Line the numbers up vertically so that the digits match the nouns that they modify. The next thing I want to warn you about, and this gets into the last phase of today's lecture, is that even though our discussions are visual, and I'm trying to downplay the role of reading, it's very important to be able to read correctly. You've got to read carefully. Language can be tricky. Language can be tricky. Let me show you how tricky language can be. Hopefully, none of you will fall for this so-called trap. But watch the problem I want to do over here. Look at this problem over here. It said, what must you add to 4 to get 6 as a sum? What must you add to 4 to get 6 as a sum? Do you see what I'm trying to do here to catch the person who's memorizing? I've done everything here to make this sound like an addition problem, haven't I? Does the word add appear here? Does the word sum appear here? Yes. But is this really an addition problem? Does this problem say add 4 and 6? Read carefully what it says. It said, what must you add to 4 to get 6 as the sum? You see, calling the blank what you must add here, what must you add to 4? 4 plus blank equals 6. See, the most common mistake here is people see the 4, the 6, the word add. They say, hey, that's easy. 6 plus 4 is 10. That's true. 6 plus 4 is 10, but that wasn't the question I asked. You found the right answer, but unfortunately it was to the wrong question, which is almost more embarrassing than getting the wrong answer to the right question. Don't settle for the right answer to the wrong question. This says 4 plus blank equals 6. That says, what must I add on to 4 to get 6? And the way that's usually written, and maybe this will seem more familiar, it's written as blank equals 6 minus 4. See, we bring the 4 onto this side and invent something called the minus sign. This is now called a subtraction problem. See, it looks like an addition problem, but it's really a subtraction problem, as I'll explain in a minute. But first, I wanted to teach you some more vocabulary. In an addition problem, the answer is called the sum. In a subtraction problem, the answer is called the difference. In an addition problem, it doesn't matter in what 2 orders the numbers appear. In a subtraction problem, it does. You can take 4 pieces of candy away from a dish that has 6 pieces of candy. But you're the miracle worker if you can take 6 pieces of candy away from a dish which has only 4. You see, addition is commutative, subtraction isn't. In subtraction, the numbers make a difference. So we give them names, and they're messy. This number here is called the minuend. Sounds like a dance, the minuet, the minuend. It's the number that's being minused from, the minuend. And this number here is called the subtrahend. And I'm not going to use that often. It's subtra means below. It's the one you're taking away, sub. And in fact, when you write it in vertical form, the minuend goes on top, the subtrahend goes on the bottom. And we read this as what? 6 minus 4 equals 2. And the way we check this is we add what? The difference to the subtrahend, and the answer should be the minuend. See, this plus this equals this. And that's very, very important. In other words, the thing that we call subtraction is in fact a form of addition. I'll come back to that again in a second. Let me just make sure you understand that. When I say 6 minus 4, I mean what? The number we add to 4 to get 6. Some of you may already have learned this. Instead of saying minus, you say take away. And take away indicates subtraction. Let me show you why you say take away, even though it's really an inverse addition problem. See, when I say to you, what must you add to 4 to get 6? Wouldn't one of the quickest ways of doing that be to put down 6 tally marks, because that's what you want to wind up with, isn't it? Then take away the 4 you already have, and what's left is what you have to add on. In other words, don't read this as 6 take away 4 is 2. Read it as what? The 4 that I crossed out plus the 2 that are still left gives me 6. And if you think that this is strange, let me show you that you've been doing subtraction this way your whole life, believe it or not. You go into a store and you buy something for $2.68, and you pay for it with a $5 bill. Unless the clerk is a Harvard graduate or has an electronic subtraction machine, how does the clerk make change? The clerk doesn't say, let's see, I'll take 268 cents away from 500 cents. What the clerk says is, what? He says 268, but he doesn't give you that. He says 268, then he puts down 2 cents and says that makes 270. Then he puts down a nickel, says that makes 275. Then he puts down a quarter and says, and 25 makes 3. Then he puts down 2 $1 bills, or a $2 bill, and says, and 2 makes 5. What did the clerk do? To subtract the $2.68 from $5, he added on to the $2.68 the amount necessary to make $5. In fact, in many cases, the clerk doesn't even remember how much change he gave you. Try it the next time you're in the store. When the clerk gives you the change, say, hey, how much change did you give me? After he gets over the shock of thinking that you're accusing him of cheating you, he'll suddenly dawn on him that unless he used the subtraction machine, he doesn't know how much change he gave you. He just added on to the 268 the amount necessary to make $5. And let's see if that works, by the way. 2 cents and 5 cents is 7 cents, and 25 cents is 32 cents, and $2 is what? $2.32, which is also 232 cents. And if you add 232 cents onto 268 cents, 2 and 8 are 10, put down the 0, carry the 1. 3 and 6 are 9, and 1 is 10, put down the 0, carry the 1. 2 and 2 are 4, and 1 is 5. Do you get the right answer? Sure you do. Sure you do. So you see, the thing that we call subtraction is a form of addition. And just to get you used to that, let me word the problem this way. I say to you, find the difference, 6,784 minus 3,621. And what this means is, what do you have to add on to 3,621 to wind up with 6,784? And by the way, you can round off again. 6,784 rounds off roughly to what? 7,000? And 3,621, see, this is a 6, that makes this a 4, is roughly 4,000. So before you begin this problem, you expect an answer of around 3,000. But watch how we do this problem. 1 digit at a time again. See, what do we have to add on to 1 to get 4? From the addition tables, we know that 1 plus 3 is 4. And the way we usually say that is 4 take away 1 is 3. Then we say 8 take away 2 is 6. 7 take away 6 is 1. 6 take away 3 is 3, which, by the way, is close to 3,000 here, 3,163. What did we do here? Why were we allowed to say 8 take away 2 is 6? Because, not just because 6 plus 2 was 8, but because 6 tens and 2 tens were 8 tens. See the denominations again? 700s take away 600s are 100. 6,000 take away 3,000 is 3,000, because 3,000 plus 3,000 is 6,000. And by the way, if you are going to round off and do what we did when we're adding, be very, very careful when you're subtracting. See, when you add, the more you have. When you're subtracting, the less you take away, the more you have. For example, if you wanted to do the same problem, see, be careful with the subtrahend. If you wanted to do this problem by locating this between upper and lower bounds, notice that 6,784 is between 6,000 and 7,000. But when you're taking away 3,621, you're going to have more left than if you took away 4,000, but less left than if you only took away 3,000. Notice the inversion with the subtrahend. You see, the 4,000, because I'm subtracting, is going to give me a smaller answer than the 3,000. You see, what this tells me is that the correct answer to this problem is going to be not just close to 3,000, but between 2,000 and 4,000. You see, if we did this the same way as we added, look what would happen over here. We'd say, okay, this number is between 6,000 and 7,000. This number is between 3,000 and 4,000. It says, okay, now we'll subtract. 6,000 take away 3,000 is 3,000. 7,000 take away 4,000 is 3,000. And now we say to somebody, whatever the answer is, it's got to be more than 3,000, but less than 3,000. That's insane. It doesn't make sense. How can something be more than 3,000 and at the same time be less than 3,000? Just be careful. All I'm trying to teach you here is don't memorize mechanically. Don't mechanically memorize. Think things through, but one step at a time. Now again, there's one more serious problem. That's going to be the whole nature of this course. Just about the time we understand something, I'm going to say, but there's one more serious problem. And no matter where we stop, there's always going to be one more serious problem. That's called life. That's called progress. It's called whatever you want to call it. But that's what happens. And let's take a look over here. Let's suppose, by the way, before I do that, let me just show you one more thing over here. I did want to come back to the change-making method here. You see, if this problem is done correctly when I subtract over here, and I got the answer 3,163, if I add this onto this, I should get this for the answer. And what I wanted you to see was that I can use change-making here the same way as I did with the $5 and the $2.68. See, I'm starting with 3,621, and I want to finish with 6,784. Now, there's lots of ways of doing this. For example, to get the 4 over here, I go from 3621 to 3624. In other words, I add a 3 on here. To get the 8 over here, I change the 2 to an 8, which is the same as adding on 6 tens, which is, I'm sorry, it's the same as adding on 6 tens. Excuse me. I'm not supposed to use my fingers, but that's 60. Then to get from here to here, from 3684 to 3784, I added on 100. And then to get from 3,784 to 6,784, I added on 3,000. And so altogether, what did I add on? 3,163. At which point you could say to me, what made you so smart that you knew to pick these numbers? The answer is I could have picked any numbers I wanted. I could have said, look, I'll start with 3,621. If I add on 9, that will bring me up to 3,630. If I add on 70, that will bring me up to 3,700. If I add on 3,000, that will bring me up to 6,700. And now if I add on 84, that will bring me up to 6,784. What did I add on here altogether? I'll leave this for you to do as an exercise, but basically all I want you to see is that no matter how you get from here to here, you're still going to be adding on 3,163. Now, with that aside out of the way, let me explain to you what the next degree of difficulty is. Suppose the next problem I gave you was subtract 3,795 from 6,123. Look what happens. You say, oh, I'll do it the way I did before. Let's see. 3 take away 5. And be careful. 3 take away 5 is not the same as 5 take away 3. How can you take 5 away from 3? What number do you add on to 5 to get 3? 5 is already bigger than 3. So we can't use that previous method. So what we do is we do the opposite of carrying. If we can trade in 10 of a denomination for one of the next higher, then certainly we can trade in 1 of a denomination for 10 of the next lower. Here's what we do. With 6,123, you see what that says? 6,000s, 100s, 2 10s, and 3 1s. I can take one of my 10s and trade that in for 10 more 1s, can't I? See, a 10 and 13 1s is the same as 23. I can take my 1/100, leaving me with none, and trade that in for 10 more tens. 1 10 and 10 10 is 11 tens. I don't have any hundreds here, but I have 6 thousands. I can take one of my thousands, leaving me with 5, and trade those in for 10 more tens. In other words, another way of writing 6,123 is to write 5,000, 10 hundreds, 11 tens, and 13 ones. Now I can take away 3,795 because 5 from 13 is 8. I get that from my tables. See, 8 plus 5 is 13. 9 from 11 is 2. 7 from 10 is 3. 3 from 5 is 2. Okay? So the answer is 2,328. Of course, this is a very messy way to do it. So watch the way we do it instead. We say we can't take 5 from 3, so we take one of our tens and trade that in for 10 more ones. See, we write the 1 very small, so it looks like 13 ones here. It makes it look like there's only one digit in this column. Then we say 5 ones from 13 ones are 8 ones. Then we say we can't take 9 tens away from 1 10, so we go to our hundreds, trade in our 1/100, leaving us with none, and getting 10 more tens. 9 tens from 11 tens is 2 tens. Then we come to the hundreds place. We say, well, we can't take 7 from 0, so I'll take one of my thousands, leaving me with 5. Trade that in for 10 hundreds. 7 from 10 is 3. Then 3,000 from 5,000 is 2,000. And there's the same 2,328 that I got this way. And by the way, I can again say what? This is the number I start with. This is the number I finish with. I can say what? What must I add on to 3,795 to get 6,123? And if you look at this sequence, you see I add on 8, then I add on 20 more, then I add on 300 more, then I add on what? 2,000 more? So altogether I've added on 2,328. There are lots of problems in the exercise set, in the text, to help you practice on that, as well as in the self-test. But I thought I would like to close today's lesson by coming back to our first subtraction problem that we did by the change-making method and showing you how we do it by the so-called borrowing method. See, the inverse of carrying is borrowing. In other words, what we say over here is, I can't take 8 from 0. I look over here, there's nothing to take away, so I borrow. It's not really borrowing, because I'm not going to give it back. I take one of my hundreds and trade that in for 10 tens. Then I take one of the 10 tens, leaving me with 9 of them, and trade those in for 10 ones. In terms of money, or whatever way you want to look at it, $500 is the same as what? 4 hundreds, 9 tens, and 10 ones. Now, in this sense, I can say what? 8 from 10 is 2, 6 from 9 is 3, 2 from 4 is 2, and there's the same answer, 232, in a much more succinct, concise way. And what I want you to notice here is that not only in today's lesson did we proceed with new concepts, but we showed how technological skill, in this sense meaning what? How the logical mind works, can help us invent recipes that allow us to do the kind of problems that we never would have had the patience to even try to do if we were still living in the world of tally marks. And that's basically how we shall proceed through the course. What I would like you to do now is to make sure you understand today's discussion. If you have any trouble at all, read the text, go through the check the main ideas, the mastery review and the study guide, self-test 2, Form A, then we'll meet again on self-test 2, Form B, if you're still having any trouble. So until next time, study hard, stay young, have fun. See you all again soon.